Facebook built Thrift. Google built protocol buffers. Both were built to solve the same problem internally, moving data between services at scale, efficiently and reliably, in a world where those services are written in different programming languages and evolve independently. Both require you to define a schema using an interface definition language. In protocol buffers, a schema looks like this: you declare message types, and inside each type you declare fields. Each field has a name, a type, and a number, called a field tag. Here's the key design decision: the binary encoding doesn't use field names. It uses field tags. When protocol buffers encodes the record, it writes the field tag number just 1, 2, or 3, instead of the string username or favorite number. The decoder looks up the tag in the schema to find the corresponding field name and type. This is what produces the dramatic space savings. The 81-byte JSON record, including all its verbose field names, becomes 33 bytes in protocol buffers. Not because the values are encoded differently, but because field names are completely absent from the wire format. Thrift offers two protocols. Binary protocol is similar to protocol buffers, 59 bytes for the same record. Compact protocol goes further: it uses variable length integer encoding to represent small numbers in fewer bytes, packs the field type and field tag into a single byte when possible, and achieves 34 bytes. 1 byte less than protocol buffers for this particular example. Both Thrift and protocol buffers generate code in your target language from the schema. The generated code handles encoding and decoding, type checking, and, critically, schema evolution. That code generation step is both their strength and their cost. You need a build step, a code generator, and the schema must be available at compile time. The schema isn't just documentation. It's the contract that makes safe evolution possible. Here's the real payoff of schema-based encoding: you can change your schema without breaking the systems that depend on it, as long as you follow the rules. The rules for field tags are what make this work. Adding a new field is safe as long as the new field is not marked required. Old code reading a new record will encounter a field tag it doesn't recognize, and it ignores it. That's forward compatibility. Old code can read new data by skipping unknown fields. New code reading an old record simply won't find the new field, and if it's optional with a default value, that's fine. That's backward compatibility. New code can read old data. Removing a field follows the same logic in reverse. You can only remove a field that was optional. And critically, you can never reuse that field tag number. If you remove field 3 and later add a completely new field with tag 3, old code that still has the old schema will read the new field as the old type, which will corrupt data silently. Tag numbers are permanent. Once a tag number is assigned and deployed, it belongs to that field forever, even after the field is removed. Changing a field's data type is possible in limited cases. Protocol buffers can change a 32-bit integer to a 64-bit integer. The decoder will zero extend or truncate as needed. Changing from int32 to string would break things. The bytes for an integer don't decode correctly as a UTF-8 string. Changing required to optional is safe for backward compatibility, but risky going forward. New code might stop providing the field, and old code that marked it required will reject those records. The mental model is this: field tags are like permanent IDs for pieces of data. Names can be refactored. Types can sometimes change. But tag numbers are forever. Avro takes a different approach entirely, and understanding why it exists requires understanding the specific problem it was designed to solve. Avro was created as part of the Hadoop project. Hadoop needs to store large amounts of data in files that many different tools can read. The problem with Thrift and protocol buffers in this context: they use field tags, which means the schema must be compiled into the code that reads the file. If you're writing analytics pipelines in many languages, maintaining generated code in all of them gets complicated. Avro's answer: no field tags. At all. The Avro schema has field names and types, but none of that information appears in the encoded bytes. The encoded record is just the values, concatenated, in the order the schema declares them. No tags, no delimiters, no type markers. An Avro encoded record without its schema is completely unreadable. It's just a sequence of bytes with no self-describing information. So how does decoding work? Avro decoding uses two schemas simultaneously: the writer schema, the schema that was in effect when the data was encoded, and the reader schema, the schema that the current code expects. These two schemas can be different. The Avro library compares them and translates between them. If a field exists in the writer's schema but not the reader's, it's ignored. If a field exists in the reader's schema but not the writer's, the reader fills it with the declared default value. If a field appears in both but with a compatible type difference, say, int to long, the library converts. This schema resolution step is more powerful than field tag-based approaches because it can handle reordered fields and renamed fields with aliases, neither of which protocol buffers supports cleanly. But it requires that the reader can always obtain the writer's schema. How does that work in practice? Avro's requirement that the reader can always find the writer's schema is elegantly solved in different ways depending on the deployment context. In large files containing many records, the writer's schema is included once at the beginning of the file. A 1 GB Avro data file stores the schema header once, then millions of records with no per record overhead. This is the Hadoop use case. The schema is in the file header, and any Avro reader can decode the file by reading the header first. In databases with individually written records, each record is stored alongside a version number. A separate schema registry maps version numbers to schemas. When a reader encounters record version 37, it looks up schema version 37 in the registry and uses that to decode. The database itself never needs to understand the record structure, just store and retrieve bytes. In streaming systems, Kafka, for example, Confluent's schema registry is the standard solution. Each message includes a magic byte and a 4-byte schema ID. The consumer looks up the schema by ID, retrieves the writer's schema, and uses it alongside its own reader's schema to decode the message. Here's a capability that distinguishes Avro from Thrift and protocol buffers. Avro schemas can be dynamically generated. Because there are no field tags, just field names, you can create an Avro schema from a database table's column names and types at runtime. Thrift and protocol buffers need schemas written by humans and compiled into code. Avro schemas can be produced programmatically from whatever metadata your system already has. That's why Avro is the encoding of choice for ETL pipelines, data warehouses, and streaming analytics contexts where the data structure is discovered from external systems rather than written by hand. The key lesson across all three formats: the choice of encoding isn't just about bytes per record. It's about what guarantees you get around schema evolution, and how well those guarantees fit your deployment context.